This video is for a short review of linear data structures. We will focus mainly on stacks, queues, and hash tables. Let's start with stacks. So to aid in the visualization, let's imagine a stack of plates following the last in, first out policy. Here we have two important operations, the push operation and the pop operation. Push is when we insert an element, pop is when we delete an element. There are several applications of stacks. We can use stacks to reverse a word. So for example, if you wanted to reverse the word hello, we can have a sequence of push operation and then a sequence of pop operation to get the reverse of a word. We can also use this for the undo mechanism in text editors. It is also used whenever there's a need to backtrack in an algorithm. We need to access the most recent data element. Another example is for retrieving intermediary evaluations in a recursive algorithm. And then stacks can also be used for algorithms with depth first search traversal. Stacks follow the last in, first out policy. And to implement the main two operations, push and pop, we also need to implement several auxiliary functions like initialization of the stack, checking if the stack is empty, or the stack is full. There are two possible implementations of stacks. We have an array implementation and a linked list implementation. Here we will discuss the advantage and disadvantage of using the two different implementations, and we will also discuss how the two operations and the auxiliary operations are implemented. Let's start with the array implementation. Let's start with the definition of an array. Array is a sequence of items of the same data type that are stored contiguously in a computer memory and made accessible by specifying a value of the array's index. There are two important properties from this definition. The first one is that it is required that the data type for all the elements is the same. So lahat integer or lahat character. The second property is the way how the array is stored in a computer memory. Data elements are stored contiguously dapat. Okay? So when we allocate an array, a fixed length n is required. So if we will use this for a stack implementation, we should know the limitation of our stack or its capacity. Ano yung maximum number of data elements that we can store in that data structure. Also, since array uses a contiguous memory allocation, physically, we have a limitation sa maximum value for our n. That is, yun yung available continuous memory na meron sa storage natin. So, running software tools that perform the defragmentation will actually help us to allow allocating bigger capacity for our stack. So, if we will use an array implementation, we also have a direct access to the data element using an index I where I is less than n or yung maximum capacity. As a stack, stack is denoted by big S from 1 to n, and we maintain a pointer called top to represent the index where the topmost element is. Since this is a stack, insertion or deletion is only restricted to the top. For the array implementation, we need to allocate the whole from 1 to n, even if the total number of elements is way below the allocated maximum capacity. And if we push an element, we push it to the top. But before we can push an element, we need to know whether the stack is full. So if top is equal to n, or equivalently if the stack is full, then we call stack overflow. So yung state when the stack is full is called stack overflow. If it's not the case, then we can increment the value for top and then we can insert our element or we can push an element x to the location of the top. For pop, we need to check if our array is empty. So if the array is empty, it's called stack underflow. And when the array is not empty, we can get the topmost element and then decrement our top pointer. So for the initialization, we can initialize a stack by just specifying that our top pointer is equal to 0. So same yan dun sa condition that we're checking if a stack is empty. What will happen if the stack is full or nagkaroon tayo ng stack overflow? We can have two possible cases. We can either issue an error or reallocate a memory. Here's an example of reversing a word using a stack. As mentioned a while ago, we can have a series of push, and then this is the corresponding value for our top if we push each character of the input word. If we pop the stack, we can get the sequence of characters in reverse order. The next one is the linked list representation or implementation of a stack. So to begin, let's have another definition ulit. Linked list is a sequence of zero or more nodes, each containing two kinds of information. So we have the data and one for the link. And the link is just a pointer to other nodes in the linked list. The advantages of linked list is that for linked list, we have a dynamic length. Pangalawa, we have arbitrary memory locations, hindi na necessarily contiguous yung space na necessary for allocation. Instead of accessing from an index, direct access, we follow the link if we have a linked list representation. And then, of course, if we have a linked list, we can also perform insertion and deletion. Here's an example of a linked list with the data and a pointer. So, to complete the implementation of a linked list as a stack, we need to define how push, pop, and the auxiliary operations are implemented if we have this representation. Okay. But before we go to the specifics of the implementation, where is the top of the stack if we have a linked list representation? Is it the head or is it the tail? And the answer is the head or A. We'll see soon enough why this is the correct answer. Let's start with the push operation. So for the push operation, if we wanted to insert a new data element X, first we call for the get node operation. This will return a structure that will allow storage of the data element and space for the pointer. Push will insert a new node and replace the head of the list by manipulating the two pointers, link and the top. After insertion, the new list will look like this with the top pointing to the new node where X is stored. Note that in this push operation, there is no need to check whether the stack is full. However, if we will pop an element from the stack or if we delete an element, it is still necessary to check whether the stack is empty. If the stack isn't empty, then we can return the value of the top node and replace the top with the next element in the list. So for the auxiliary operation, for initialization, we set the top equal to lambda. This is the same condition that we use for checking if we have an empty stack. For fullness test, we don't check for stack overflow, but our get node will issue an error if wala ng space available. And lastly, let's compare the two implementations of stack. For the array, it's easier to implement and it's also easier to access the content of the array. But for array implementation, we need to identify some fixed n at the onset. So, dapat alam na natin si n, which is yung capacity. If we know the maximum capacity of the stack, then it's okay to use the array implementation. However, if we know that n is very large, also difficult din to get a contiguous memory allocation that is free dun sa physical storage device natin. On the other hand, for the linked list representation, actually ina-address niya yung problem ni array implementation by having arbitrary memory location. And we also don't need to allocate it in the beginning. So, mas marami nga lang steps that we need to do to pop an element because we need to do some link traversal to replace the location of the top node. Now let's move on to queues. As a visualization, we can imagine an actual queue of customers waiting for a service. It follows a first in, first out policy, and in the data structure, the first element added to the queue will be the first one to be removed. And when we insert an element, it's called enqueue. And when we delete an element from the front, we call it the queue. Similar to the auxiliary operations needed for stack, we also have some auxiliary operations for queue. We have the initialize is empty and is full. We have an additional auxiliary operation here. We call it pick. For the pick, we can get access to the element in the front, pero we don't need to delete it. Okay, so queues are applicable to operations where the order matter. So for instance, queues can be used for task scheduling. We can also use queues for managing data in transit from one type of storage to another through memory buffers. And queues can be used by greedy algorithms. Well, we will discuss more of this in the next module, but to give an idea, greedy algorithms construct a solution piece by piece. And we use queues to maintain the sequence of greedy choices. In general, we can use queues if we have an algorithm working on a sorted list. In this use case, we have a priority queue. And another example is for the implementation of breadth first search traversal. So similar to a stack, we can also implement a queue using an array and using a linked list. But for the array implementation, we have two variants. We have the straight and the circular queue. Let's start with the straight queues. So here we have an abstract data type and a corresponding implementation using straight queue. So in a queue, we have the front and the rear. We delete here's the front and then we insert sa rear part. In an array implementation, not necessarily ang front ay nasa index 1 or nandun sa pinaka mas mababang index. Kasi sometimes when we try to insert, we delete, we insert, we delete, ang nangyayari is nagmo-move yung data natin sa gitna ng array representation na n yung fixed na size. Here's the pseudocode for the enqueue procedure. The first condition checks whether the value of rear is equal to n. And if this is the case, either we have a full queue or may space pa naman. Pero we have unused space na nandito sa left side of the front index. If ever we still have a space, we can move the elements of the queue to the leftmost side of the straight queue. Then we can proceed with the insertion afterwards. And if ever this condition is not true, we can skip this part and continue with the following code. So when we insert, we increment the rear and we add the data element here. The queue is much simpler because we just need to check whether the queue is empty. Otherwise, return the element in front. Deletion takes constant time. However, for insertion, pwedeng mangyari yung worst case scenario where we need to move the elements. So how exactly can we implement the move queue? Okay, so here's the procedure. What it does first is to check whether the front is 0. And if that's the case, there's no need to move the queue because wala nang space. Otherwise, we move each element of the queue to the leftmost side of the straight queue. So the running time of this move queue procedure is in theta n or in linear time. So imagine if we always need to do this. Diba? So the second variant of the queue array implementation solves this problem by using a circular queue. In this representation, we no longer have to move the elements if rear is equal to n. However, we need to do some pointer arithmetic to allow circular access to the array. So here's a corresponding pseudocode for the NQ operation. And here's the corresponding pseudocode for the queue operation. So note that we have some pointer arithmetic here just to make sure that while we have an array na linear naman talaga, we can access it like a circular array. So another thing that we need to note is these two conditions. So it's important to distinguish if our array is empty or if full na yung capacity. We can do this by sparing one space. So to be able to distinguish the two cases, if we have an empty, we can have this condition. If full na, we have this condition. So yung spare natin dito is necessary to distinguish the two cases. So if we allocate n elements in a circular queue, actually n minus 1 lang yung capacity that we can use from that allocation. Okay, so that's it for the circular queues. Let's move on to the linked list representation. So in a normal linked list, we have a head and a tail. The corresponding queue implementation is intuitive because we can set the head as the front and the tail as the rear. The linked list implementation also doesn't have to deal with the move queue. So, yeah, so beneficial yung paggamit ng linked list, similar to the circular queue. But the downside is that since we are using a list, we need twice the size of the array. One for the data and one for the pointer. Yung nire-return ni getNode kasi is always twice the size of the data. But of course, may advantage then because we don't require the data to reside in a contiguous space. Okay. So the initialization for the queue is similar to that of a stack. We simply set the front be equal to lambda. When we enqueue, we call the function getNode. So this will provide us a space for the storage of the data and the pointer. Bibigay siya sa atin ng error if ever wala ng available space for the new node. We have two possible cases here. The first case is if we are adding an element from an empty queue. Okay? If that's the case, yung front and rear natin both points to the new node. Otherwise, if may existing na laman na, we just need to add the node dun sa rear part. So, magkakaroon tayo ng another node dito and then we update the value of rear. For the queue, first we need to check if may laman pa ba yung queue. Otherwise, we return the data in the front and then just update the value of front. Okay, so as a summary, we showed 3 possible implementations. And as much as possible, we wanted to avoid the move operation. And we ended up with 2 possible cases, yung circular queue and the linked list implementation. If we expect the maximum number of elements in our queue or predicted na yung capacity ng queue natin, then circular queue is the best case. But if we can't predict how much space we need, then linked list is a safe implementation. But there's a downside then. We just need to spare twice as much the actual number of elements in our queue. And for the last linear data structure, we have the hash table. We will tackle more about hash tables in part 2, but for this lecture, we will give the fundamentals. In an ideal world, we have unlimited storage and we can store and access the elements in constant time. However, reality is we have limited space and the total number of possible data to be stored is way much larger than the available space that we have. So hash table provides a mapping such that we can access and store the elements in U sub k as fast as possible by mapping it to a corresponding index in a table with limited space, say m. So in creating a hash table, we have three concerns. The first one is that the key or data content is not necessarily numeric, and so we need the mapping from non-numeric to numeric such that we can use it as an input to retrieve a particular location I. The next concern is finding a good hash function such that the number of collision is less. Ang alternative description nun is that we can have a uniform distribution from U sub k or k to all possible values of I. And then the third is when a collision happens, what is our collision resolution? So for our answer to the first concern, we present here three possible conversion. The first one is, for example, we have keys, which is a non-numeric key. If we wanted to convert it to a number, we can treat each character as a decimal from its order in the alphabet. So K here is equivalent to 11, E is 5, Y is 25, and then S is 19. Okay? So that's one. The next option is to treat each string as an encoding using an alphabet of size 26. We can convert any string of this representation to its decimal counterpart. Okay, so the third one is the generalization of the second approach by expanding the allowed character set, and in fact we can use all the ASCII recognizable alphabet. So for this example, we can use its corresponding ASCII code and then convert it to a decimal representation. Here we show the corresponding numerical representation of the non-numeric keys if we follow the third example in the previous slide. Let's go back to the second concern and let's give a criteria for a good hash function. Our hash function is good if it can be calculated very fast, even though our hash function table requires less comparison compared to the arrays or even binary trees. Computing for h of k usually requires some computational time. So for example, if we have a polynomial of degree n for our h of k, we know that from our previous lecture, computing for p of x will take linear time. So that's not a good hash function. The next criteria is it should minimize collision. The collision happens when two distinct keys get hashed to the same index. This is bound to happen because of the pigeonhole principle, but there are some cases that we can still minimize this. One example is if we use the division method. So for the division method, we have h of k equal to k mod m. This will ensure that the index will still be in the valid indices of the hash table. We do have a couple of criteria for choosing m. M should not be even because if M is even, even k will hash even i's, add k will hash to odd indices. Also, we should avoid setting m as a power of the radix of a computer because keys with same ending character will hash to the same location. Next is we should avoid setting m of the form 2 to the I plus minus j, where j is some small integer, because setting uh, this as our m will have keys having the same character set to hash to the same location. So the suggested value for m, if we avoid this, is actually a prime number that is not too close to some power of 2. So here's an example m. Here we have m equal to 59. So here we can see that some keys hash to the same location in the table pero hindi naman sobra-sobra na. There are certain parts uh, of the hash table na mas marami compared to the other. The second approach is called the multiplication method. The idea behind this hash function is based on the following theorem. So here's a graphical representation of the theorem that says that if we use the suggested hash function, and that is equivalent to this form, and with a good value for theta, we will have a uniform distribution of keys in the line segment, thus avoiding collision. So, using the multiplication method, we have this hash table. So, this is the same set of keys we showed a while ago na gumamit ng division method. So, for the multiplicative method, we can see na mas kaunti na yung elements that hash to the same position. Since collision are inevitable, we will also discuss some collision resolution such as chaining, open addressing. So there are two types of open addressing, the linear probing and double hashing. For chaining, we create a linked list for all the keys hashed to the same location. And if you wanted to insert a new element in the hash table, we create a node containing the key, data, and a storage for the link. If the resulting index from the hash table points to a lambda, that means the element is the first data in that location, then just insert the new node and create a fresh linked list. But if a collision happens, we simply extend the linked list. We can access the content of the hash table by first computing the hash function and then traversing the linked list. The second method is through open addressing. The idea is to utilize empty spots in the hash table. When a particular key is hashed to a non-empty location, the open addressing uses a parameter s to check the I minus s iteratively until an empty cell is found. Here is an example of a key hashed to 9, I equal to 9. With s equal to 3, we show that uh, we have a sequence of steps to look for an open address. In this example, it took 5 steps before we can insert k sub j to its final location. The advantage of this method is that we do not allocate extra storage for keys that collide. However, the disadvantage is the extra probing step whenever we insert or whenever we access that element again. So for open addressing, if we have s equal to 1, we call it the linear probing. The next type is when the probing uses another hash function, say h prime of k. This is used to address the possible clustering of keys if we use linear probing.